Okay, we'll start from the current slide. And here's Jalen, right? Huh? Lauren, sorry. There you are. Okay. Anyone else come in since the code roll? Okay. May turn on the projector today. All right. We are now recording. Let me go over just a couple of things. My office hours have now changed for the second mini-term. First mini-term, my physical science class on Tuesday, Thursday started at 1:15. So all I had for office hours on Tuesdays and Thursdays was my lunch hour, 12:15 to 1:15. That's all the time I was in the office for more than a few minutes from 8 in the morning until 5:45 in the evening. Okay? However, with the second mini-term, Minnie's here. Now the second mini-term has started. Today's physical science class doesn't start until 3:15. Reason is the automotive students, some of them need it for their program of study. In fact, that's why we offer it on mini-terms, because we have Ford, GM, and Toyota dealership programs, and those students are on co-ops. They are in school for 8 weeks and at the dealership for 8 weeks. And their first year students are in school the first 8 weeks, at the dealership the second 8 weeks. The second year students are at the dealership the first 8 weeks and on campus for the second 8 weeks. They just got back this week, and those are the ones who need the class. However, their block programs in the automotive program go until 3 o'clock. So therefore, I can't start the physical science class until 3:15, which gives me 2 hours of office hours from 1:15 to 3:15 Tuesday and Thursday afternoon. That's good. I'm here till 8 o'clock at night. Not quite as good, but no way around it. Okay. As far as I know, I'll be back on Birmingham campus on Friday like I was last Friday, and hopefully there won't be many of interruptions there like there were the last few weeks. Okay, I can't think of anything else. Any of you have any questions before we get started today? Oh, I did this poorly. I didn't set up my...
Were you at your office yesterday?
I'm sorry?
You said that I could come to my test yesterday, but were you at your office?
Okay, I was in the office from 3:15 to 5:15.
And you said it was down
265, yeah. Go down almost to the end of the hall, the lower level, second floor. The last door on the left is the stairwell. And next to that is my office door on the left. Right across the hall from the orientation classroom.
Maybe it was by the stairwell.
Yeah, between the mechanical room and the stairwell, that's my office.
I checked the wrong room then.
Pardon me?
I checked the wrong room then.
Yeah, because I was there. Actually, I was there until about 9 or 9:15 last evening. So I was there all afternoon from 3:15 on. Well, 3:30 on, because I had to get Blackboard set up. Okay.
Well, I'm going to try and do this tomorrow.
Okay.
And you said I can start at 1.
What's that?
You said I can start at 1. You said you were being there at 1.
Today?
No, like Mondays and Wednesdays.
Mondays and Wednesdays, 3:15 to 5:15. And Tuesday and Thursday, 1:15 to 3:15. And Friday, all morning on Friday, on Birmingham campus. Okay, I think this is where we begin. Let me go back one. Okay, I think we did that one. Okay. All right. Any other questions? Some people came in. Trey? Okay. Anyone else come in sets a call roll? I apologize for my voice. I went to the UAB football game Saturday, so got 2 minutes to start. Okay, we're at the bottom of page 123. We're at chapter 2, polynomial and rational functions. 2.2, polynomial functions of higher degree. Okay, and we're at the bottom of that first page, 123. We'll soon be at the top of the next page. And here's Danielle. Okay. Now, what we were talking about are characteristics and graphs of polynomial functions. Give me 2 features of polynomial functions. The graph of them.
We'll have a curve.
Yeah, they will be curved. Let me get Chris here. Okay? And what do you mean by curved? No points, no cusp, nice, smooth curves. That smoothness, the other part, continuous. Polynomial functions are smooth and continuous. Now we're going to deal with some other issues of polynomial functions that affect the graphing. So using the features that we will be presenting, coupled with your knowledge of point plotting, intercepts, symmetry, that kind of stuff, you should be able to make reasonably accurate sketches by hand. Of course, if you have a graphing calculator, you can see pretty well. However, just yesterday, or let's see, when was it? I graded it. Probably Friday, I was grading one of my better students' Cal 2 test, and there was one problem. Where did he get these limits for his integral? And I just sketched out the thing and noticed they weren't anywhere close. And so yesterday after class, I was talking with him about it because he really hurt his grade, not just that problem, but others. So where did she get these? He said, got it off my graphing calculator. Some things are easy, not that hard to graph, and easier to keep from making a mistake than punching in a number and you not realize it. Is it Josh? Okay. So, graphing calculators are great, but sometimes the sketches by hand will give you a lot better insight. Because it's doing the thinking and the work. If you do it, you start seeing and realizing more about the function. Now, this turns to the top of page 124. The polynomial functions that have the simplest graphs are monomials of the polynomial form f of x equals x to the n. These are called the power functions. Okay? So n is an integer is counting numbers greater than 0. That makes them the natural numbers or the counting numbers. 1, 2, 3, 4, 5. Okay? These are your simplest polynomial functions. Okay? Also called power functions. Now, we did some of these back when we did the parent functions in the last chapter. This is sort of a review. If you look at this, figure 22.9a, you see that when n is even, this is y is equal to x squared, the gray curve, is a parabola. This is y is equal to x fourth, a quadratic function, I guess you would call it. A few things to notice. Now, these are the power functions. Sorry about my throat. Both of them have 3 points in common. Okay? Whoops. Courtney, that's what I was going to say. Okay, anyone else come in since I called off? Okay. Negative 1, 1, 0, 0, and 1, 1. If you did x to the 6th, x to the 8th, x to the 24th, x to the 72nd, they would all have those 3 points in common. Okay.
Corner.
Second. Corner. Got it. Okay. Anyone else come in since the call draw? Now. Okay, I've heard someone else. What else do you notice about these? Well,
It looks like they're on the x-axis.
what?
It looks like they're at zero for an extended period of time on the x-axis.
Okay.
It looks like they're at zero. It looks like they're on the x-axis.
Right.
Lying on the x-axis.
Right. And that's, very good. That's one of the things I was going to point out next. The higher the exponent, the steeper the curves are here, but the flatter they are there. Okay? Now, they never are on the x-axis except at 0, 0. But they get very close for a lot further out. So if you had to the 72nd power, it would almost look like a definite U there. Okay? So, the other thing to note, when x goes negative, because you're raising it to an even power, the y is going positive. When x goes positive, raising it to any power, the y is going to go positive. So these are what I call the up and up. And speaking of up and up, here's TEF. Okay. All right. So that's a characteristic of a power function whose exponent is even. Okay? They go in the same direction. Now, what determines that direction? The sign of the leading term. If that sign is positive, they're going positive. If that sign is negative, though, they're both going down. Okay? Now, when n is odd, you have these characteristics. Here it is, the gray curve here is y is equal to x cubed, and here the black curve is y is equal to x to the fifth. Again, the larger the exponent, the flatter it is in the middle. It's never perfectly flat. It just approaches zero more quickly out here and creeps up to zero, only crossing at 0, 0. They're just barely greater than 0 here until it goes up. But past -1 and -1 and +1, +1, the higher the exponent, the steeper it is. The smaller the exponent, the less steep. Okay? And if you did x to the 27th power, it would follow the same pattern, steeper here, flatter here, steeper there. Okay. But notice here, for odd exponents, these power functions go in opposite directions. Because when x is negative, so is the y. When x is positive, so is the y. As long as the coefficient is positive. And those are all we're looking at right now. But if you do a negative, then it flips it over. And for negative x's, we'll go to positive y's. Positive x's will go to negative y's. Okay? We'll get to that in a later slide. Does this make sense? Now, these are the power functions. In just a little while, we will talk about more general polynomial functions, not monomials, but having lots of terms in them. What it boils down to, though, is that leading term. Okay? If the leading term has an even exponent, in the long run, they're going the same direction. If that leading term has an odd exponent, they're going in opposite directions. Okay? Down and up for positive leading terms, and up and down for lower for the negative leading coefficient. So we'll get there in a minute. Just a little bit of look ahead. Moreover, the graph of the value of n, the greater the value of n, the flatter the graph near the origin. Here's example 1. It says, sketch the graph of each function. All right. I know you can probably hardly hear me, and probably it's not picking up sound too well, but I feel like I'm yelling because I don't have any voice, and I'm having to really strain to get the any volume at all. Well, all right. Now, and again, I was explaining to people who were here before, I got a loaner computer from the IT department on Friday. They said mine was to be ready then. They didn't have it anywhere close. It's a smaller screen for me to write on, and then within the screen, it only gives me a smaller box. So I'm going to write as small as I can, but it's going to look like I'm writing really big because it's a small screen being blown up. So it looks like I'm wasting space. I can't write any smaller on here with this ionizing pen and make it very legible. So let's do our best to graph this function. Okay, that's supposed to be a straight line. That's supposed to be a straight line. All right, let's tick off a few points. The origin, 1, 2, 3, 4, 5, 6. Negative 1, 2, 3, 4, 5, 6. Positive 1, 2, 3, 4, 5, 6. Negative 1, 2, 3, 4, 5. Okay. What can you tell me about f of x equals negative x to the fifth?
You want a point, or it's going to be flipped on the regular function?
Okay.
It's going to be flipped. It's going to be opposite of the regular function
Because it's negative. Okay, so tell me a point to plot.
0, 0.
0, 0 sounds like a wiener. Okay.
Negative 1, 1.
Okay. If you go negative 1 on x, negative 1 to the fifth power is negative 1. But then you negate that and you go positive 1. Okay? And 1, negative 1. Because 1 to the fifth power is 1. Negate that and you go to negative 1. Okay, now my graph isn't spaced too well. If you try to do the next point, 2, yeah, you're in a huge number. Positive 32 here, negative 32 there. So basically this is coming down really steeply here and then flattens out pretty much and then goes down real steep again. That's basically what it looks like. Like you say, it's a reflection across the x-axis, okay, on the power function x to the fifth. Now, I made it look like these are exactly 0 here. They're not. It comes down and gets very close to 0 and stays awfully close to 0, creeping towards 0, only crosses right there, and then it's just slightly below 0, slightly below 0, and finally goes down. It goes down steeply. Okay? You want to do the other one in a different color? What color would you like? Red. Okay? How would I plot h of x? Okay? Ebony. There you go. All right. Anyone else come in, Sister Control? Okay. How would you go about plotting h of x? X plus 1 to the fourth. Give me some characteristics of that. All right, here's the one. Second.
What's your question?
How do I plot h of x is equal
You're
to
going to
x?
go to the left one time.
Left one space,
And then it's going to face up. And it's going to be the U.
like a parabola, only flatter at the bottom. You're absolutely right. So we'll go left one, okay? And then to the right of that, we go right one, up one. To the left of it, we go right one, up one. The next one would be right 2 from the origin there, the vertex, up. Second? I can't hear. 16, yeah, it would go up 16, off scale. So basically, we're coming down very sharply, flattening out here and then going back up very sharply. Probably didn't flatten out enough there. That's how that one looks. It's a power function, but x plus 1, which means you shift to the left. Make sense?
Yes.
Okay. Let's delete that then and see how they do it. Well, here's the first one. Good for them. They got it right. They copied us. Because it's an odd function, the graph is similar to that of y is equal to x cubed, the cubic function, but it's flatter near the origin and steeper past plus or minus 1. Okay? The negative coefficient flips it across the x-axis. Okay? The graph of h of x is equal to x plus 1 to the 4th power, shown here, is left shift by 1 unit, and then it looks like the graph of y is equal to x to the 4th, which looks a lot like y is equal to x squared. The difference is it's a little flatter here and steeper past plus or minus 1. Make sense? Okay. All right, by the way, there is a checkpoint right after the example. Always a good idea to do the checkpoints as soon as you can after class is over. Now, the book calls this next thing the leading coefficient text. Okay? I call it fungus here. Okay? I've got to find, there you are. Okay. Has anyone else come in since I come wrong? Okay? Frankly, I call it the leading term test. Not just the leading coefficient, the leading term. If you know everything about the leading term, you know the vast majority of what you need to know about the function. Okay? Or at least its general pattern. In example 1, note that both graphs eventually rise or fall toward infinity without bound as x moves to the left or to the right, okay? As x goes here, y's are going to some infinity, always. So if x is going to an infinity, y is going to some infinity, maybe the same one or a different one, but infinitely high or low. So whether the graph of a polynomial function eventually rises or falls is determined by the function's degree as the leading exponent, the exponent of the leading term, whether it's even or odd, and also by the sign of the leading coefficient, positive or negative. So you see, all that is in the leading term. So why call it leading coefficient test? Because the degree has nothing to do with the coefficient. That's the term. So the leading term test is what I like to call it. Okay? Now, what we're going to be talking about here is what most books call the end behavior. Okay? What's happening for very small x's or very large x's? What is the function doing? Okay? For polynomial functions, they're going to infinity, either plus or minus here or plus or minus here. As x goes to negative infinity, y is going either to plus or minus infinity. As x goes to positive infinity, y is going either to plus or minus infinity. It's taking off and going without bound. Okay? So as x moves without bound left to right, the graph of the polynomial function. Okay? Here's that standard polynomial function. A sub n. The n here just tells you which coefficient this is. This is the coefficient that goes with x to the nth power. That n is part of the problem. Okay? X raised to that power. The a sub n tells you this is the coefficient that goes with that power. So this n is just a marker. That n is part of the problem. So the next one will be plus a to the n minus 1, sub n minus 1, x to the n minus 1. And then you keep counting down the x's till you get to x, a to the first, x to the first, a to the 0, x to the 0, which is 1. Okay? So this function, this x moves either right or left, it eventually rises or falls. Now, here's what's happening. When n is odd, okay, that leading, the degree of the polynomial, degree of the leading term is odd, then your f of x is going to opposite infinities. We just don't know which is which yet. Okay? So if n is odd and the leading coefficient, a sub n, is positive, then when x gets very large, y gets very large. When x gets very small, y gets very small. Because you're taking a large number and raising it to a large power. If that number's positive, it goes positive. If n is odd and you're raising that to a large power, and the x is negative, then that's a very large negative number. Okay? So they're always like this. Okay? If a is positive, it's like this. If a is negative, it's like that. For odd n's. Okay? Now, what goes on in here, we don't know. Right now, we're not really caring about it. We're only looking at the end behavior. Now, on quizzes and on tests, you'll see this show up. And it will go in different forms. Okay? I usually start as x goes one way, f of x is going to something. As x goes the other way, f of x is doing something. Okay? So you'll see as x goes blank, f of x goes blank. As x goes blank, f of x goes blank. When you see those problems for polynomial functions, guess what? Every one of those blanks has an infinity in it. Every one for polynomial functions. Okay? Now for x's, one's going to be a negative infinity and one's going to be a positive infinity. So guess what? You can fill in those two blanks and get them right every time. Because that's what I'm asking for. What happens as x goes negative? What happens as x goes positive? So there's two blanks you should get right every time. And the symbol you get in all four of the blanks is an infinity. Okay? All you have to figure out is the sign that goes with f here and the sign that goes with the f there. That's all there is to it. If that n is odd, the signs are going to be opposite. If the a is positive, the sign is going to be the same as the x sign. Negative, negative, positive, positive. However, if that a is negative, notice they're going in opposite directions. So as x goes to negative infinity, f of x is going to some infinity. As x goes to positive infinity, f of x is going to some infinity. Infinity everywhere. This one's negative, that one's positive for x. What do the y's do? For an odd exponent, okay, in odd, okay, then they're going in opposite directions. So 1 plus and 1 minus, they go opposite to what the x is. If x is going negative, you take a negative x, raise it to an odd power, it's going to be negative. However, if a is negative, that's going to make it go positive. If you take a large positive number, raise it to a large an odd exponent, that's still going to be positive until you multiply it by a negative number, and then it flips it over and makes it negative. So those are like this, okay? So if a is positive, you're like this. If a is negative, you're like that. If the exponents are odd, they're going in opposite directions. Okay? Now for evens, they're going in the same direction. Okay? And again, you have the same four issues. As x goes somewhere, f of x goes somewhere. As x goes somewhere, f of x goes somewhere. One of these x is going negative infinity, one's going to positive infinity. Those two you get right every time, right? Good. Now, what do the f's do? They're all going to an infinity. If these are polynomial functions, they're going to an infinity. So all four of those are infinities. Okay? Now, if n is even, these two infinities are in the same direction. What direction? If A is positive, they're up. If A is negative, they're down. If N is even, that's what it is. So as x goes to negative infinity, in even a positive, then f of x is positive. As x goes to positive infinity, in even a positive, f of x is still positive. Okay? In here, all sorts of things could be happening. Who cares right now? We'll care later, but right now, all we care about is the end behavior. Okay? It's on the up and up. If n is even, and the a is negative, down, down. Okay? Down for negative, down for positive. Okay? As x is very large. So here are your 4 blanks. Blank, 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 blank. Okay? Negative infinity for x, positive infinity for x. Those two you get right every time. This time, since it's even n, but a negative a, both of these are negative infinities. Negative, negative. Okay? All this tells you is the end behavior, but this is important to know. And you'll see later how we put that in right at the beginning when we start graphing these polynomial functions. All right, let's do a few. Describe the right hand and the left hand behavior. In other words, the end behavior of the graph of each function. You just tell me what it is. I'm going to put the blanks here for you. Woo! All right. As x goes to blank, f of x goes to blank. As x goes to blank, f of x goes to blank. Okay? We'll do that for all 3 of these. Okay, from the first one. As x goes where?
Negative.
Negative what?
Infinity.
Infinity. Negative infinity. What does this do? Positive infinity. Because x cubed would be negative, but you negate that, it goes positive. As x goes to
Negative.
positive infinity, what does f do?
Negative.
It goes to negative infinity. You got it. Okay? Does everybody see that? As x goes to negative infinity, f of x goes to positive infinity. As x goes to positive infinity, f of x goes to negative infinity. My infinities look pretty lousy, but there they are. Okay, you tell me what to fill in here. X goes to positive infinity, f going where?
Positive.
Positive infinity. As x goes to negative infinity,
Negative.
positive because it's an even exponent. Raise a negative number to an even power, and what do you get? A positive number. Okay? So that's as x goes to negative infinity, f of x is going to positive infinity. As x goes to positive infinity, f of x is also going to positive infinity. Now, it doesn't feel fair that we ignore these other terms, does it? So let's just think about it. I'm not even going to get close to infinity. Let's just do 10. Okay? As x goes to negative 10, what is x cubed? Ten times 10 times 10.
Oh, that's what you want. 10 times 10 times 10.
1,000. This goes to 10. Okay? It swamps it. Okay? And that's just a 10. What if I went to 100? Or a million? You know the numbers get huge. Yeah, these take over for large x's, negative or positive. So that's what I usually do. Nothing else. Just think, well, if I have a negative 10 here, x cubed becomes negative 1,000. Negate that, it's positive 1,000. It's going to positive infinity. As x goes to positive infinity, positive 10, that would be positive 1,000. Negate it, it goes negative. Okay. So what happens here? As x goes to negative infinity,
Goes
up.
up.
Positive infinity.
Up.
As x goes to positive infinity, it goes up also because you're raising it to an even power. Negative 10 to the fourth power is negative times negative times negative times negative. It's positive. Any even number of negative signs is positive. That would be 10,000. Who cares about what these are doing? Nothing's going to come close to that. How about this one? As x goes to negative infinity, what does f go? Say again? Negative infinity. Because say a negative 10 raised to the fifth power is negative because it's odd exponents. Okay? And that would be 100,000. Negative 100,000. As x goes to the positive infinity, positive infinity. Fantastic. Y'all see how that works? All right. Let's clear this. Well, I don't think I need to clear it. Whoa, that's not what I want to do. I can't breathe. Okay, here's the first one. Who cares about what's going on in the middle? We do later. But because the degree is odd, all we're interested in the end behavior. The leading coefficient is negative. As x goes negative, f goes positive. As x goes positive, f goes negative. That's what we're interested in. Now, if you're going to graph it like they didn't ask us to, what's the easiest point to figure out? Okay, put x equals 0, and what do you get? Y is equal to 0, so it goes to the origin. Okay? Next easy thing to do would be to factor this. If you factored it, factor out a minus x, right? And that would be minus x times x minus 2, no, x minus 4, and x squared minus 4. That's x plus 2, x minus 2. So there's your two other x intercepts. Y-intercept 0, 0. That's also x-intercept plus or minus 2 of the other ones. Because we know the end behavior, we have to start here, go down, up, down. It helps you in your graphic. Okay? We'll get to that part later. Here was the second one, x fourth. What else do you notice about this function? Both of what?
I guess they're called the humps.
Yeah, the humps. Okay, we call them max and min. Right? Extrema. Okay, the extrema is the same. Oh, say again? Oh, yeah, he's right. It's not the y-axis, so it's the origin. Because these are odd. It's an odd function because both of your exponents are odd. So sure enough, it's symmetric about the origin. So that's why the humps are similar, but in opposite directions. How about this one? Yeah, it reflects across the y because it's an even function. Absolutely. Okay? So we know something else about it. Okay? What we're interested in here is the end behavior, up and up. Negative x's raised to the fourth power are positive, very big. Positive x's raised to the fourth power are positive and very big because the leading coefficient is positive. Okay? What's an easy point to figure out? 0, 4. X equals 0, y is equal to 4. There it is. Now, this one isn't quite as easy to, actually it's not bad to factor. Because this would be x squared minus 4 times x squared minus 1. And both of those are difference of two perfect squares. X plus 1 times x minus 1, x plus 4 times x plus 2 times x minus 2. Minus 2, minus 1, plus 2, plus 1. So that would have been pretty easy to do as well. Most of them are not that easy. Okay. Let's do the next one. Okay. What can you tell me about that one?
They're odd.
Odd. Wow, they gave us Most functions are going to be neither. Okay, so they gave us 3. 2 of them are odd, 1 was even. Strange but true. Yeah, they reflect across the origin. And what's the y-intercept? Oh, do in behavior. Negative. When x goes negative, y is going negative, x goes positive, y goes positive. Because it's an odd exponent, positive coefficient. Leading term test. 0, 0 is there. If you had factored that, the x times x to the 4th minus 1, well, x to the 4th minus 1 factors to be x squared plus 1 times x squared minus 1. X squared minus 1 factors to be x plus 1 times x minus 1. So sure enough, there's your other two x-intercepts. The x equals 0 is the third one. The other don't have zeros, so x squared plus 1 does have what factor and x x squared minus 1. Okay. So anyway. All right, does that make sense? They didn't tell you the graphic, they just told you to do in behavior, but this shows how that helps. So in example 2, note that the leading term test tells you only whether the graph eventually rises or falls to the right or left. That's all it tells you. But that's important. The other characteristics of the graph that we were just looking at, the intercepts, the minimum, maximum values, must be determined by other tests. We just went over some of them. Okay. That was example 2. So, what we were doing, we were finding the zeros, which is another name for the x-intercepts. Because the zeros are where the function is 0, and function is, f of x is? What is f of x? Always is y. Where the y is 0 is the x-axis. So another name for real zeros will be your x-intercepts. Okay? Of polynomial functions. You'll also use things like roots or solutions, or there's lots of names for those zeros. All right. It can be shown for a polynomial function of degree n. What does that mean?
Any number.
Let's say again.
Any number.
Any
Real.
positive, n, positive whole number. Counting numbers, 1, 2, 3, 4, 5. Doesn't even count 0. Doesn't count negatives. No fractions, no decimals. Only the positive counting numbers. But where do we find what the degree is? Where do you find the n? The maximum exponent of your variable. The term of the maximum exponent, that's your n. Okay. It can be shown for a function of degree n, the following statements are true. The function has, at most, n real zeros. It may not have n, but at most it does. Let's go back and see if that fit. How many, what was the n here? 5. How many real zeros? 3. But it had at least, it could have had up to 5, it only had 3. What's your n here? How many zeros? Don't look for any more, there aren't any. Can't have more than 4. What's your n? 3. How many zeros? Don't look for any more. It can't have them. Okay? So it can have up to n, but it may not have n. Okay? So that's the first thing. That gives you the maximum number of real zeros you have. Now notice the zeros don't have to be counting numbers or even integers. Those all were. They don't have to be. The graph of F has at most n minus 1 turning points, and this is what you're picking up. A turning point is also called a relative minimum, a relative maximum. Another name for it is an extremum. Okay? These are the points at which the graph changes from increasing to decreasing or from decreasing to increasing. That's a turning point. And they're always, for polynomial functions, smooth and continuous, rounded. Okay, never pointed. Okay, let's go back and see. What was your n? 5. What would be the most number of turning points? Huh? 4. N minus 1. How many did we have? 2. Okay, that's less than 4. Good. This one, what's your n? Maximum number of turning points? 3. How many do we have? 1, 2, 3. 3 turning points. We've reached the max. This one, what's the n? What's the maximum number of turning points? Say again? 2. Okay, I can't hear. And here's 1, there's 1. We reached the max. Can't have any more than that. May have fewer, but can't have any more. Okay? All right. Finding the zeros of the polynomial functions is one of the most important problems in algebra. All right? Seems like that should have been on the slide by itself. There is a strong interplay between the graphical and the algebraic approaches to this problem. Okay? Graphical approach, where it crosses the x-axis, also called the x-intercepts, the zeros, the solutions, the roots. Okay? Real zero is a polynomial function. When f of x is a polynomial function, a is a real number, the following statements are equivalent. If x is equal to a, is a zero of the polynomial function. Yeah, zero of the function. That's equivalent to saying x equal a is a solution or a root of the polynomial equation, f of x equals 0, because the 0 in the function is where the y is equal to 0. That's what it means. So these two are equivalent statements. But not only that, subtract a from both sides, and you get x minus a is a factor of that polynomial f every time. So on the other hand, if you find out it's a factor, add a to both sides and you got a 0 or a solution. The other thing, like I said before, x equal a, y is equal to 0. A 0 is an x-intercept of that graph. If you know any one of these, you know all 4 of them. If you know it's a 0, it's also a solution to that equation. It's a factor of the function, and it's a 0 is the intercept. You know it's an intercept, all of those are true. Any one of them, they're all true. Make sense? Pretty exciting stuff, isn't it? All right. So, here, find all the real zeros of that function. What you reckon we're going to do? Oh, he's doing it algebraically. I thought he wanted to draw a graph. No, I like algebraic too. It's much easier. Okay, so what did you say? I would factor out a minus 2x squared, because I like to get rid of that minus sign if I can. I can't get rid of it, but isolate it. Okay, what's left? X squared. Yeah, that's the only problem with factoring out the minus. You got to remember to change signs. Minus 1. Okay? Are you through factoring? Oh, how do you do that? So this is, don't forget this one. Minus 2x squared times x plus 1 times x minus 1. Okay? You factored completely. Okay? Now what do we do? Set it equal to 0. Remember this rule back here? It's a 0 if it's a solution for this. So set that function equal to 0, but in the factored form, set it equal to 0. And so set this equal to 0 then, and what does that tell you? Either x equals 0. Say again? Okay, let me go back. I can't hear everything you're saying, sorry. What were you saying? Either minus 2x squared is equal to 0, or x plus 1 is equal to 0, or x minus 1 is equal to 0, okay? What's going to solve this equation? 0. X equals 0 has got to be there. In fact, x equals 0 or x equals 0. Okay? If you factor that completely, negative 2 times x times x, negative 2 will never equal to 0. X could be 0 or x could be 0. That's what we call a double root. Okay? Almost like double McGuff. No, it's not the same. Okay? How about the second one? X equals negative 1. The third one? X equals 1. Guess what? You just found the real zeros. How many could we have? You thought? Up to 4. We found 3. Why? Because this one was a double 0. Okay? So we really found 4. 0, 0, 1, negative 1. Okay? But we only count 0 ones. Okay. How about the maximum number of turning points?
3.
It could have up to 3. Okay? So I think we probably want to draft the function, don't you?
No.
Oh, let's see. Whoops. All right. Now, where I like to begin to graph is where we began today. And what was that? In behavior. What's the in behavior for this problem? Okay. What's the function doing? Negative infinity. So x going to positive infinity? Still going negative. So here's how I illustrate that. It's going down here and down here. That's my in behavior. That's how I start the function, the graph. I know it's got to be going down in the extremes. Okay? Next thing we did, we found our 3 zeros. 0, 0, 1, 0, and negative 1, 0. Okay, now, how about another really easy point to find? Y-intercept. That's even easier than the x's. And what do we do for it? Set. It happens to be 0, 0, 2. There it is. You can have many x-intercepts. How many can you have? Up to 4 in this side. Up to whatever your n is. But y's? 1 and only 1. For a polynomial function, you're always going to have a y-intercept. Because polynomial functions are smooth and continuous. If they're continuous, and they're starting here and going there, you're going to have to cross the y-axis. Some places they can only cross it once. Right? Okay, and there we found it already. 0, 0. All right. Now I can give a hint on what this is going to look like. It's going down here. Whoops, wrong. Okay, let me try that again. Here's the key. Now I'm jumping ahead. Okay? Because this is a double 0. At every 0, it crosses the axis. Since that's a double 0, it goes across, but then it crosses back. So that actually stays on the same side. That's called, anytime you have a multiplicity, you hang around 0 a little longer. So it does like this, like this, like this. Now that's ugly, but it's going to be something like that. Now, why did I show that? I may not have the dimensions right, but is the general view of it right? What kind of function is this? Even. It should be the same on both sides. And sure enough, I tried to draw it that way. Now it may be squished down, it may be expanded up, but it should be the same on both sides. Okay, let's clear this out of the way. Any questions before I clear it? All right. So to find the zeros, you set it equal to 0. Okay? When you set it equal to 0, you factor. They did the first factorization just like you did. Remove the common monomial factors. If you have a leading minus sign, get out. it out with the others. Okay? You want the rest of it to be positive on the leading term. Okay? Then you factor a little bit more. That's exactly what we got. Those are real zeros are x equals 0, x equals positive 1, x equals negative 1. The x equals 0 happens to be a double zero. Okay? Multiplicity of 2. Because the function is a fourth degree polynomial, function can have at most 3 turning points. I forgot to ask you that. How about ours? Whoa, where was it? Oh, I erased it, didn't I? Yeah. Okay. I had them. Okay. Okay. Ah, there it is. Not quite as pretty as mine, but close, right? Okay. Mine went up too high on mine. That's what you got. It crosses at this 0. It hangs around and goes back up at this one and crosses it down. Okay? I'm going to give you a hint ahead of time. If that multiplicity is odd, which x minus 1, that was to the first power, that crosses. If it's even, x squared, it kisses and goes back up. If it's odd but greater than 1, then it comes down, hangs around, and then goes down. Just like a cubic function or a fifth function. This is a lot like a parabola or a fourth one. So you see right there at 0, it does just about what the function would have done. And then at 1 it crosses. All right. Does that make sense? So in example 3, note that because the exponent is greater than 1, it was okay. The exponent for the factor negative 2x squared, it yields a repeated 0 at x equals 0. Okay? Those two different zeros there. Okay? If any old factor, not just x squared, but x minus a is raised to the kth power and k is greater than 1, then we say you have a repeated 0 at x equals a. Remember? The factor is x minus a, and 0 is x equals a. Okay? So, you see it there. If that k is greater than 1, you have a multiplicity of k. If that k is odd, then the graph crosses the x-axis at x equals a. If that's a large k, like 3, it comes down sort of like a cubic function, but still crosses. To the fifth, it comes down, still crosses to the seventh. Okay, always crosses. But if the k is even, like to the fourth, it comes down, hangs around, but goes back up. Just like a power function would. It touches the x-axis, but does not cross it. I like to say it kisses the x-axis. Okay. And that's the x equal a. So if it's even, it doesn't cross. If it's odd, k is odd, it does cross. And that works even if k is 1. It says greater than 1, still works if k is 1. If k is 1, it crosses. It just doesn't hang around. So, to graph polynomial functions, use the fact that polynomial functions can change signs only at the zeros. They don't have to change signs, but it's the only place it can change signs. Why? Because polynomial functions have 2 features. What are they? Continuous and smooth. And if it's a continuous function, and f is positive here and negative there, guess what? It's going to cross. It becomes 0 somewhere in between. It can't jump over it because that wouldn't be smooth. Okay? Now, it may cross 7 times, but it's going to do it. So the graph of polynomial, you use the fact that the function, the y value, can only change signs and its zeros. Because 2 consecutive zeros, between 2 consecutive zeros, the polynomial must be either entirely positive or entirely negative. All right? If you have a 0 here and the next 0 is here, it's going to either be like this or like that. It can't cross in between because if it crossed in between, it would be consecutive zeros, right? So it's got to, okay? And it can't jump over because it's continuous, okay? So it's either all positive or all negative in between consecutive zeros. That means that when you put the real zeros of the polynomial function in order on the x-axis, because of x-intercepts, remember? They divide the real number line into intervals in which the function has no sign change. So if you have 0 here and here and here and here, it's all positive here, all positive and negative here, all negative and positive here, but in between, it has no sign changes in between. Now, sure, you can have a 0 here, here, and here. It can be positive and positive there. That's no problem if it has a multiplicity of even multiplicity of that 0. Okay. These resulting intervals are called test intervals. So all you have to do, if you find the zeros, pick some value in between the zeros, put it in the function. If it's positive, you know it's positive everywhere in there. If it's negative, it's negative everywhere in there. Okay? So, let's put that to the test. Whoa. We did example 3. They skipped example 4. In fact, I shouldn't have even. Yeah. They skipped 4 and 5. So let's go back and do 4. I think that has the most room right there. Sketch a graph of f of x is equal to 3x to the 4th minus 4x cubed. Sketch the graph of it. So we'll draw our little axes here. All right. I'll tick off a few points. Okay. If you're sketching the graph, where's a good place to start? What? End behavior. I like it. What is the end behavior of this one? Both ways? Both of them positive. So it's on the up and up. Okay? There's the end behavior. Something like that. Going up in both places. You have very large negative x's, raised to the 4th power becomes very positive, very, very positive, multiplied by positive, stays positive. Very positive, positive x's, raised to the 4th power, very, very, very positive, multiplied by positive is positive. Yeah, there's on the up and up. So what's the next thing we do? Okay, how do you get it? Which one you say? Okay, f of x equals 0. Good, next choice. Okay. Factor out what? No, keep the leading term positive. X cubed, and what does that leave us with? 3x minus what? 4. That's equal to 0. Okay? What does that tell us? Second? Yeah, okay. So x cubed equals 0, or 3x minus 4 equals 0. X equals 0, or, second? 4/3. All right. There are only 2 zeros. How many were we expecting? Up to 4, but this is a triple right here. So there's your other 2. Okay? 0, 0, 0. Okay? And 4/3. Well, 4/3 is 1 1/3. So there's a 0, and there's a 0. Okay? Those are only 2 zeros. Now, what can you tell me about this one? Multiplicity of 3. So what does it do? Crosses or kisses? Crosses, because it's odd multiplicity. But it hangs around a while, doesn't it? Okay? So since it can't have any more, it can't change signs anywhere in here, right? And it's up here. That means it's coming down here and it's going to cross here, but because it's that cube, make it look sort of like a cubic function. That sort of SE curve in it. But then it has to go back up here because it winds up going up. So it has to be negative in between here. So there is how it looks. Something like this. Comes down here. Well, if I can get it to draw. Hangs around there just a little while, then goes back up. Because that's multiplicity of 1, it just goes straight through it. Multiplicity of 3, it hangs around there a little bit longer. Say again? Okay, there's some other points there. If you plug in x equals 1, the f of x is going to be negative 1. So 1, negative 1 would be right there. Okay, so you can make it go through that. Yeah, that would be better. You could plug in a negative 1 and see what you get. That would still be a 3. This would be a plus 4, so that would be 7. 1, 2, 3, 4, 5, 6, 7. So it should be right up there. Right there. And I came pretty close to it. Okay. Good deal. You should plot a few more points. Actually, what he did a test point here. He went between these two zeros to see what it was going to be. He found out it was negative. We knew that anyway because of the end behavior and the fact that it crosses. It had to be negative, but he confirmed it. And then you could pick a point there, positively do that, and you could pick a point. You didn't pick a point. I just drew some stuff there. We could do 2 there, be a huge number, but you could do it. 2 to the 4th is 16 times 3 is 48 minus 32 would be 16, I think. So it's positive, way positive. I'm not going up fast enough. Okay. See how that works? If you take a look in the book, bottom page 128, you see that it's, they almost drew it as pretty as mine, right? Close, but no cigars. Okay. Let's do example 5. Oh, so sad. We can't do example 5 today. Get over it, folks. Okay. All right, we'll begin with example 5 next time. Oh, but the good news is we can do some homework exercises. Okay? Do any of, I would say do all of 9 through 14. The odds are in the back, so check the answers on the odds. Those are fun problems. You're matching up the graph with the exercise. Okay? You can do either 15 or 17. Both of those are on countcheck.com, but countview.com has 17 on it. You can do any of the odds 19 to 27. Ooh. But all you're asking for is end behavior. You don't have to do any graphing or anything, I don't think. All those odds are on councheck.com. Number 21 is on countview.com. It says using technology. If you have a graphing calculator, try 29 or 31. Guess what? You can probably do a lot of that without a graphing calculator, but give a look. Then on 33 to 47, finding real zeros. All those are on countcheck.com. 43 is on countview.com. And then 49 or 51 uses technology to do the same type thing. Okay, the rest of them we'll pick up next time. All right? Good deal. We'll see you on Thursday. Sorry about my throat. Huh?
Oh, you say your
Throat, yeah, it's a horse. Okay. All right, you